Thank you for the nice introduction and welcome to my today's presentation. So as the content of today's presentation, I would like to show you a short overview and the motivation about the research topic. Then I would like to introduce my test and measurement technology. Afterwards, I'll give a short introduction in the applied lifetime prediction method StressLife. Afterwards, I'll show you my experimental results. And at the end, I'll give you a summary and outlook of today's talk. So what is the idea behind the research project? As you all know, the determination and calculation of SN curves is often associated with a huge amount of specimens and lots of tests. So there's lots of costs and time needed for them. Therefore, lifetime prediction methods have been developed. But the problem with those lifetime prediction methods is that they are often limited to the transition between the low cycle and high cycle fatigue regime and to the high cycle fatigue regime itself and for test frequencies of high hertz. Therefore, investigations of the transition between the high cycle fatigue regime and the very high cycle fatigue regime are also complicated due to the long test durations. Therefore, we started to use a resonant testing rig, which allows us to do higher testing frequency fatigue tests. The question now is, can these lifetime prediction methods also be applied for these higher testing frequencies? So my goal for today's talk is to present you the validation of the applicability of the lifetime prediction method StressLife for two testing frequencies of 80 and 260 Hertz. But as my title also says, I'm doing a temperature correction of the electrical resistance. Why do I do that? Therefore, we have a short look at the determination of the electrical resistance. It consists of the electric specificity, the length, and the area of my specimen. According to Matheson's law, the resistivity contains two parts. On the one side, there's the temperature-dependent part due to the scattering of electrons by phonons. On the other side, I have a temperature-independent part due to the scattering from static lattice effects. Because of the high testing frequencies, because of the high test frequency, we do the tests without compression air cooling. We have lots of self-heating effects. Therefore, I'll have additional to the temperature to the frequency effect, I have also a temperature effect. Therefore, we do a temperature correction of the electrical resistance. How do we do that? Therefore, we just did a little testing setup. Here you can see a fatigue specimen in an unloaded state. Then we'll have those electrodes, which we use for power supply. We use Kelvin clamps to measure the voltage drop, also in use with a shunt resistance, which we can then calculate the electrical resistance during Ohm's law. We have a heating device. This heating device has an opening here, which is very small but big enough so we can use an IR camera to measure the surface in the test area of our fatigue specimens. If the heating device is activated, we'll get this curve, and afterwards, if it's deactivated, it's also a cooling graph, which we can get. So with the setup, we can determine the temperature-dependent part of this heating curve according to this equation. And with that, we can calculate the temperature-corrected electrical resistance. We say that the total electrical resistance consists of this temperature-dependent part and the temperature-independent part. And so we can calculate the temperature-independent part. The measurement setup for the fatigue test is as the following. We're using a resonant testing rig type Microtron by the company Rosenberger Prüfmaschinen AG, which is also advertised in the lobby, I can say. You can see it here, and it's usually an identical measurement setup as for the temperature resistance behavior measurement, except that we are doing here the power supply directly by the clamping tools, because those electrodes would vibrate during the high frequency, and we remove the heating device. We also did some residual stress measurements. Therefore, we used X-ray diffraction examination using Seifert space XID TS4 by the company XRD Eigenmann GmbH. Therefore, we used the center of gravity method for 70%, which consists of acquiring a diffraction spectrum, so the intensities versus the two theta angles. There we get the peak shifts, and we can calculate the residual stresses using Hooke's law. As to theta angular range, we used the 211 HKL plane for the investigated ferritic perlitic steel SAE 1045 in a normalized condition. If this is our fatigue specimen, we also did in total 3 measurements per direction, and then calculated the average. As already mentioned, we applied the stress lifetime prediction method. Therefore, we do in the first step a load increase test with non-destructive technique-related measurement techniques. We'll get here the material response, which we are averaging per load level. We plot the corresponding material response with the respective stress amplitude in a Morrow equivalent plot. There we separate between elastic and plastic material behavior to calculate some exponents B and C. We use them in also with 2 constant amplitude tests to calculate the coefficients B and C. With these fatigue data, we can estimate the material response of a third constant amplitude test, and then we have everything we need to calculate an SN curve according to stress life. As a result, here's the results of the first load increase test. That's for 80 Hertz. Starting stress amplitude was here 180 megapascal with 5 megapascal load increase steps for every 180,000 steps. You see here the change in temperature, the change of directly measured electrical resistance, and the change in the temperature-corrected electrical resistance. These load increase tests are very good to determine the fatigue limit of the material, because you can look where the first material response occurs, which is here for a stress amplitude of 220 megapascal. For 260 Hertz, this is the corresponding graph for this. And here we can already see an increase in lifetime for the material response, which here occurs the first at 240 megapascal. And the load step of failures also shifted to higher stress amplitude. So we have here the estimation of the fatigue limit, which increases with the testing frequency, and also the general fatigue life extensions itself. From this, we take, like shown, the average material response for the lifetime prediction method. We also use the data of 2 constant amplitude tests per test frequency. So here's the cyclic deformation curves based on the directly measured electrical resistance and the temperature-corrected electrical resistance. We can see here that the incubation interval, so the material response for 260 Hertz is significantly delayed in comparison to the 80 Hertz tests. And the point of maximum softening is also always after 50% of the total fatigue lifetime at 260 Hertz. It's also observable that the cyclic hardening occurs over a very long cycle range for 80 Hertz. That's of about 100,000 cycles, while it is for 260 Hertz only for about 30,000 to 40,000. With those fatigue data, we can calculate our SN curves here for 80 and 260 Hertz based on the measured change in temperature, and also for the change in the temperature-corrected electrical resistance. These 2 graphs I want to summarize in one final, where we can compare both. And for all graphs, we can say that the data points are well covered for both test frequencies. Also, we have a similar progression for the curves based on this temperature-corrected electrical resistance, which is not observable for the curves based on the change in temperature. So where does this deviation come from? In general, we have to look at competing processes. On the one side, we have processes which lower the dislocation mobility. Because of the increased test frequency, the accumulation of the necessary cumulative shear stresses in the structure to start the dislocation mobility is delayed. On the other side, we have processes which increase the dislocation mobility. because we have this huge energy input into the specimen in a shorter time with an increased testing frequency, we have a higher amount of dissipated thermal energy, which cannot radiate across our specimens quickly enough. So the proportion of internally stored heat increases, and the air convention itself is not sufficient enough for the heat dissipation. So we have thermally induced dislocation movement. So as already mentioned, we have the frequency effect on the one side and the temperature effect on the other side, which we did this temperature correction on the electrical resistance to have a material response which doesn't have this temperature effect, or that doesn't show this temperature effect. We also did some residual stress measurement like mentioned. Therefore, we estimate the different fatigue life stages according to our calculated SN curves. And after the last stage, the specimens were fatigued until failure to recalculate then the real fatigue life stage. So if we say we wanted to start at 50% of the fatigue lifetime, and afterwards then we can say, okay, no, it wasn't at 15%, it was already at 23. So we did also measurements in two directions, on one side in the tangential direction and on the axial direction. And we showed that the direction doesn't really matter because both values are quite similar and the progression of the curves itself too. We can see that the degradation of the residual stresses at 80 Hertz are the greatest at around 20% of the total fatigue lifetime, which also is in correspondence to the cyclic deformation curves I've shown before. The degradation of the residual stresses for 260 Hertz are comparatively low at the beginning of the fatigue lifetime. This is due to the dislocation mobility, which is restricted due to the higher testing frequency. So we have here a slower residual stress degradation. To summarize my presentation, we can say that the stress life method is also usable for testing frequencies above 5 Hertz. The frequency effect is clearly observable in the cyclic deformation curves with regard to the duration of the cyclic hardening and in general increase in the fatigue lifetime. Also, we had a temperature influence due to the immense frequency related self-heating effects of our specimens. And therefore, we did the temperature correction of the electrical resistance. Also, there were no differences in residual stress measurements in axial and tangential direction. And the degradation of the residual stress corresponds with the cyclic deformation curves. And as future investigations were planned, these are on the one side, we want to apply further lifetime prediction methods for higher testing frequencies. And our goal is to calculate SN curves for different test frequencies just based on one test frequency database. Then I would like to thank you for your attention, and I'm open for your questions.